So we saw in physics part 1 that potential energy is something that you create when you do work against a conservative force. So let's take a look at a counterexample, the work done against friction. So when I push this eraser, I'm doing work against the frictional force, but the work that I did is basically gone. As far as mechanical energy is concerned, it's vanished. It got turned into heat. It warmed up the table very slightly. So no matter how long I wait, this thing is not going to bounce back. Kinetic energy is not going to magically reappear. It's basically gone. So it's different in the case of conservative forces. So in physics 2.1, you basically saw two different types of conservative forces, forces with which potential energy can be associated. One is a spring and the other is gravity. So I don't have those fancy springs or those curly things like a slinky or something. I have the next best thing. I have a little bungee cord, a small rubber band. So look at what happens. When I push on this, I did work. It seems like the energy is gone. But if I let go, the kinetic energy reappears. So my work got stored as potential energy. So the force of a spring, or in this case a bungee cord, is a reversible force. It's a conservative force. Another example is gravity. So if I pick up this eraser and raise it through a certain height, I did work. At the end of this process, there's no kinetic energy because the gravity did negative work. I did work against gravity. Gravity stores that as potential energy. So when I let go, kinetic energy reappeared. So gravity was the second example of a conservative force. You have a retrievable process. So the same is the case with electric forces. It's a conservative force. So watch what happens. With this positive charge, if I fix it in place and I move another positive charge towards it, it seems like the energy is gone, but when I let go, the kinetic energy reappears. So it's just like compressing a spring. It's a reversible force. It's a conservative force. So look at what happens. You see the energy comes back. So that's why when you bring two positive charges close together, like these two over here, there is a repulsive force between them, and it stores that energy just like a compressed spring. You have a positive potential energy. On the other hand, if you have a plus and a minus charge, let's look at what happens over here. I don't have to do work. The negative is attracted by the positive anyway, but I have to do work to move this away from that positive charge. It wants to go back. So in this case, we have negative potential energy. You have to put work in to separate that. You have a situation with negative potential energy. Okay, so now let's get quantitative. So the amount of potential energy a system has is the amount of work that is needed to create that situation. So here you have this eraser on my hand. I do a certain amount of work to lift it up. That's the gravitational potential energy. Is the energy I had to put in against the force of gravity. Is the work done by the external force. So the increase in potential energy is the work done by the external force from my hand, for example. So the work, of course, is F dot delta R. And this is for a fixed, a constant F. If F is changing, this turns into an integral. But let's get to that later. So in the case of gravity, what do we have? So the increase in gravitational potential when you lift something up is your external force, the force coming from a hand, that's doing the work to put in the potential energy, times the displacement. So the amount of force I have to exert to lift a weight is just the weight, which is mg. And in this particular context, the delta R, the displacement, is the height. So when I lift something through a certain height, the potential energy that I add to it is mgh. So that's the case of gravity. How does it look for the electric force? So in the electric case, here's my fixed positive charge, like this thing over here. And then I have my movable positive charge. That's this charge over here. When I move this thing over through a displacement delta R, I do work. How much work do I do? Well, the work is force times the displacement. So delta R times the force is the work that I do. That's the increase in the potential energy, the delta U right here. And how much is that force? Is the electric force between two charges. So if you have two charges, two positive charges, the force is given by Coulomb's law, and that's K Q1 Q2 over R squared. So that's the force. And notice that the force is in the same direction as the displacement. This is not the electric force, by the way. This is the work done by the external force, my hand. That force is in the same direction as delta R. The electric force may be opposite, but this is in the same direction. So the work done is this is the force and that's the displacement. They're in the same direction. This is the increase in the potential energy. But that's to move it from here to here by a tiny amount. What happens if you have a charge sitting here and the other one is brought all the way from infinity over there? You're doing a lot more work, but it's more than that. In this case, the force is not constant, it's variable. So you have to use integration. No matter, the end result is very simple. It's almost like this delta R cancel one of the R, and you end up with K, Q1, Q2 over just 1 R. So let's see what that is. So here's the derivation. If you're not a lover of calculus, that's okay. You can skip this part. But that basically leads to this. So you can't just multiply this delta R and R. Since you're going all the way from infinity, the force is changing all the time. It's a variable force. So you do have to integrate it. Nevertheless, this is the final result. The potential energy of two plus charges brought together, one is fixed, you bring the one all the way from infinity to this point, there is repulsion between them all the time. So as a result, you build up potential energy. It's like compressing a spring. How much is that potential energy? The closer you get it, the more the potential energy. You have to do more work to bring them closer. And of course, if the charges are bigger, you'll have more potential energy. So not surprisingly, you have that previous constant K here, the Coulomb's constant. You have the first charge, the second charge, and then you have R in the bottom here. So the closer they are, the bigger the potential energy. And this is the expression for the potential energy of 2 point charges separated by a distance R. Next up, you have the rule for adding potentials. Because of the law of the superposition of electric forces, the fact that you can add the electric forces together and pretend you have a single force of that magnitude, this leads to the result that the potential energies for multiple charges, they can be added scalarly. So what do we mean by that? Let's say you have two charges, Q1 and Q2, and these are fixed. So for example, here's a Q1 and there's a Q2. You say they're pushing each other away, but let's hold them in place. So how they got to be together at the moment, that's not our problem. But we have a third positive charge over here. We bring that in from infinity. So we are pushing against the top charge, the Q1, and we're pushing against the bottom charge, the Q2. All the time, these things are pushing back. So you have to do work against both of these. So the potential energy you would have had just pushing against the first one, plus the potential energy you would have had if you pushed only against the second one over here, the third charge acquires the potential energy, which is the algebraic sum, the scalar sum of those two potential energies. So in symbolic form, what that means is the potential energy of Q3, the third one, in the presence of the first and the second charge is equal to each of these calculated separately. And each of these expressions, the potential energy between a pair of charges, Q1 and Q3, that's given by this equation over here, the formula for the potential energy. So the unit for electric potential energy is the same as the unit for any potential energy, or any energy for that matter. So our standard MKSA unit for energy is joule, symbolized by a capital J. Next up, we have the concept of electric potential. Not potential energy, but potential. The electric potential is like the potential to have potential energy. What do we mean by that? So let's take a step back and see what it did for the when you introduced the concept of an electric field. So the electric force between 2 point charges, that's K, Q1, Q2 over R squared. Instead of thinking of the two forces, the two charges exerting a force on each other, we pretended that the first charge was creating a field around it, and then the second charge was getting influenced by that field. It's like a fan blowing air, and the air is hitting this, instead of thinking of the forces directly between them. In fact, there's a reason to believe that's the actual situation. So equation-wise, what we did then was to break up the force equation, the K, Q1, Q2 over R squared, into an electric field. So the first part over here, this part over here, this is the electric field created by charge Q1. Then, so E is equal to K Q1 over R squared. And then this electric field, it hits the second charge Q2, and hence you have a force. If you combine these two equations together, you put the electric field back in here, you recover Coulomb's law for the force between the two charges. So something similar can be done in the case of the electric potential energy. Just as here the electric field was a property of that point in space, that location, if you had a charge Q2 in that location, it was basically the victim of that electric field. But E is a field, it's a point in space with a certain property. So similarly, the potential energy expression K Q1 Q2 over R, it can be broken up. We can think of this first part over here. This is the potential created by the charge Q1. So V is K Q1 over R, and now Q2 is sitting in that potential, so it gets hit by the potential V and it acquires a potential energy. So we know that if you bring two charges together from infinity, they have a potential energy given by this whole expression here, K Q1 Q2 over R. You can think of the first charge as creating something around it, a field basically. When you move the second charge into the location, it acquires that value. And so the potential created by this first charge is this first part here, K Q1 over R. The second charge, because it's in that potential V, it acquires a potential energy. When you combine these two things, you recover the expression for the electric potential energy of 2 point charges. So this thing over here, the V that is created by the first charge, that's referred to as the electric potential. So when you have a charge over here, it has the potential to give potential energy to a second charge brought in its vicinity. But there's no second charge, there's no potential energy, but this still has the potential to give potential energy to a second charge when brought there. So at this location here, at that distance, K Q1 over R, you have the electric potential V. When you put a second charge there, that V times this charge Q2, that's the potential energy. And these two combined basically give you this equation over here. So this is the concept of electric potential. Any place where you have an electric potential, to bring a charge from infinity to that point, is going to acquire an energy given by that potential times Q2. And the unit for electric potential is a volt, the symbol for which is V, which is kind of unfortunate because it can be confused with the symbol for the physical quantity electric potential. The next property, remember, is that since the potential energies due to multiple charges could be added together, similarly the potentials from multiple charges can be added together. So in other words, if you have a charge over here, this is Q1 and this is Q2, and if you brought this thing over here, it acquired a certain potential energy. Then if you divide that by its charge, that's the potential. So this point in space over here, both of these are pushing any positive charge that wants to get over here is going to get pushed away by both of these charges. So as a result, both of them contribute to the potential energy. So this location, the potential is going to basically add up together in an algebraic manner. So to hopefully make sense of what was just said, let's do a quick example. So you have two charges, Q1 and Q2, and just like these two good guys over here, except they're not equal. This one is 3 coulombs, that one is 5 coulombs. The question is, what's the potential at this location over here? So these 2 point charges are separated by 3 meters, and then from the Q2 to this location in space, that is 4 meters. So there's nothing there, just an empty point in space. But it has the potential to give you potential energy. In other words, if you were to bring a charge over here, it would acquire a potential energy. How much? This potential that we're about to calculate multiplied by the value of this charge over here. So let's go ahead and calculate the potential over here. So to solve this, we want to find the potential at this point, which I've labeled as P. So you have the potential created by Q1 at this location P, and the one created by the potential created by Q2. You can just add them scalarly, including the sign. Here both are actually positive. One could have been negative, or both could have been negative. But in any case, the V at point P that you have over here, that's the V created by Q1, this first charge, plus the V caused by Q2, this second charge. You calculate the potentials for each of these and simply add them scalarly, which means algebraically. So here you have K, Q1 is 3 coulombs divided by 7. 7 meters is the distance from Q1 to P. Then plus the second potential, which is V caused by Q2, V due to Q2. That's K Q2 over 4. Q2 is 5 coulombs. 4 is the distance from there to there. That's the R that you have in that previous equation. Crunch this out, you get K times 1.68 volts. So K, you may recall, this is Coulomb's constant. This is 9 times 10 to the 9. So this is the voltage that you have, the potential that you have at that particular location. So now let's add 2 more parts to this question. So we found the electric potential at point P. So at point P, you have electric potential there. What does it mean? If you were to bring a charge and put it over there, it'll acquire potential energy. What is that potential? You find the potential due to Q1 and Q2 at point P, you add them up. So each potential is KQ over R. Q1 is 3 coulombs. The distance R is 7, 3 plus 4 all the way there. Then for the second charge, Q2, its charge is 5 coulombs, so that's 5. The distance is just 4 from there to there. And so you add these two up, you get K times 1.68. K is 9 times 10 to the 9. So this combination, 9 times 10 to the 9 times 1.68, that's the electric potential at point P, which means if you were to place, bring another charge over there, the potential energy it would acquire is this V times the Q. So next up, let's add these two parts to this question. What is that potential energy? So if you had a negative 7 coulomb charge and you brought that all the way to point P, what would its potential energy be? Not potential, potential energy at point P. And third, how much work is required? So you saw you have to push things to bring them to a certain location when there's a phase opposing charge. How much work is required to move it into position, to move it over there? So let's do the first, the part B first. So there's the result. The potential energy is the charge times the potential. The charge is minus 7 coulombs. The potential energy we found, the potential we found over here was 1.68, 9 times 10 to the 9. So here we put those three things together. This gives you the potential energy, 1.06 10 to the 11 joule. So that's the meaning of electric potential and potential energy. And finally, the last part, C here, what's the work required to move that negative charge into position? So we had those two positive charges. Remember, and you calculated the potential here, which was that huge number, 9 times 10 to the 9 times 1.68 volts over here. And we want to bring this negative charge into position. So how much work do you have to do? How much do you have to struggle to bring this into position? So the work required externally is equal to potential energy. Remember, like when you're pushing this positive charge over here, you have to do work to bring it here. It's like compressing a spring. So that work is exactly what leads to the potential energy. But so therefore that work is the potential energy. But in this case, the potential energy was negative because you have minus 7 coulombs. What does that mean? How can you have a negative amount of work required? That's because when it's positive, it's repelling. But when it's negative, it's not repelling, it's attracting. You don't have to do work. You get work out of it. So as this thing is sliding down into negative potential energy, you can get work out of it. And that's how hydroelectricity works. You have water at a height, it falls over a dam, goes through some turbines and stuff like that. Because it's losing potential energy, you get work out of it. So anytime you have a situation with negative potential energy, you don't have to do work to get there. You get work out of it. And that's why the work done externally is actually negative. And that's the meaning of that sign. Next up, you have the concept of potential difference, also known as voltage. In many situations, especially in electrical circuits, you don't know what the absolute actual potential is at one location versus another. You only know the difference. An example is when you buy a battery that kind of looks like this. You have a negative potential here relative to this end over here. This end is positive relative to that, but each one could be roughly plus 1000 volts. What the battery guarantees is that the potential difference between this end and that end, that is 1.5 volts. So there are many situations in which a potential difference is defined. So you have two metal plates or two ends of the battery, etc. They have a certain, they have different potentials, but it's only the difference that's meaningful. But a lot of times the charge is going from one potential to the other, so the change in energy only depends on the difference in the potential, not the absolute potential. So here's an example that kind of illustrates that. So here you have two metal plates. This one is charged to minus 300 volts, this one to plus 300 volts. So you have a potential difference over here. These are the absolute potential. But as you'll see, it's only the difference that matters. So between these two plates, you have a metal ball. That ball is charged to minus 2 microcoulombs. And it's touching this 300 volt negative plate over here. So because the charge is negative, and this potential over here is negative, and this side over here is positive, this plate is going to pull, and the left plate is going to push. So you end up with a force F in this direction. So what we want to find is what is the acceleration of this charge as it moves from here to here. And let's find the final energy and the final speed of this thing. So to do this calculation, we need to know the mass of this ball over here. Let's give it a mass. How about 0.1 grams? Okay, so that's its mass. So you have a little sphere over here. It's holding a charge of minus 2 microcoulombs. The mass is 0.1 grams. It's going to get pushed by this one, by this plate here. It's going to get pulled by this plate here. Opposites attract, likes repel, and all of that. So it's going to get, it's going to feel a force. It's going to accelerate. We want to find. So the question is, what's the speed and the final kinetic energy as this ball makes it from the left to the right hand side? So let's find that. So here's that question somewhat neatly written up. So here's the picture of this, of what's going on, and what you're trying to find is, as this ball goes from left to right over here, find the final speed and the kinetic energy as it goes from the left to the right. So now let's do it. So we'll solve this using the concept of potential energy and energy conservation. So as the charge goes from there to there, you have a conservative system. That's why we could define the potential energy in the first place. In a conservative system, like if you drop an object through a height, the kinetic energy gets converted to potential energy and vice versa. So here, applying energy conservation, the kinetic energy plus the potential energy here equals the kinetic plus potential energy here. So as it goes across, is speeding up, it's going to lose potential energy and gain kinetic energy, but the total is constant. You have energy conservation, going back to physics part 1. So this states that the energy conservation states that the total E is constant. The total E is made up of kinetic energy plus potential energy. You can have more than one or two moving things, so as a result is the sum. In this case, it's simpler. You have just one thing that's moving across, so its kinetic plus its potential is constant. So the initial potential plus the initial kinetic, this equals the final potential plus the final kinetic. So these sums are equal because the total energy is constant. Now the initial kinetic is 0. This ball was at rest before it kind of took off and was forced to the right over here. So this is equal to 0. So the final kinetic energy is going to be the initial potential energy minus the final energy. So just rearranging this equation and solving for Kf, the final kinetic energy, that's equal to Ui minus Uf. Notice that that's actually minus the change in U, because usually the change is the after minus the before. This is the before minus the after. So this is minus delta U, minus the change in the potential energy. But as we saw earlier, the potential energy can be linked to the potential. So the potential at two places, your minus 300 and plus 300 here, the difference in potential called the voltage, in this case 600 volt, that can be linked to the change in the potential energy. So the change in U is equal to the change in potential times the charge. And so the minus sign was just carried over from before. Now the charge is actually negative. It's a minus 2 microcoulomb. So you put that minus 2 in here, and so that minus and minus will cancel out. Now as far as the potential is concerned, the final potential is 300. The initial is minus 300. So 300 minus 300 will be 600, which gives you 1200 joule. I just realized that the charge is not 2 coulomb, it's 2 microcoulombs. So this should get, so there should be times 10 to the minus 6 for micro here. So this should be multiplied by 10 to the minus 6. So it's a lot less than a joule actually. So that's the energy that the thing picked up as it sped up from the left to the right. And this is this introduces or confirms the concept of electric potential, how it connects to the potential energy. Charge times potential is the potential energy. So think of potential as that location, that electric plate, having the potential to give potential energy to something that's on it. In this case, that little blue ball with carrying that minus 2 microcoulomb charge. So this is an illustration of how you use electric potential and potential energy.